So, are there any questions from what we did last time? Let me, let's begin just to remind you, because this is really the crucial point here. We said, let's try and examine a differential equation. And we took this because things were nice and easy. And we said, how does y behave near x equals 0? Okay. And what we are doing here is called local analysis, because we're examining the solution of a differential equation not for all x, but for x near 0. Okay? Now, in fact, let's see, you worked, Tibor, you worked over a practice, this this y prime equals e to the minus x times y, right?
Right.
Studied.
Yeah.
Right. So you, as for practice, a few days ago, you looked at, what was it? It was y prime prime equals e to the minus x times y, something like that? Okay, you looked at that equation, and you tried to solve it in two ways. You know that that x equals 0 is an ordinary point or a regular point of this equation, right? Because this function here has a Taylor series about x equals 0. It's a smooth function at x equals 0. And what you did was you found a solution y of x of the form a sub n x to the n. This is local analysis. This solution is valid near x equals 0. Furthermore, an equal sign is allowed there because that's a Taylor series. And a Taylor series converges, and this Taylor series is equal to that function. Okay, so nothing fancy going on here. Okay? But this was local analysis. Okay? Meaning that as you moved away from x equals 0, the Taylor series became less and less useful. And you compared the result with doing a perturbative calculation, right? And you found that the perturbative calculation was much more global, was useful in a much more global sense. So you found, one, a Taylor series, and two, a perturbation series, okay? You were able to express y of x as the sum from n equals 0 to infinity, epsilon to the n, yn, okay, where you inserted an epsilon into this differential equation, okay, where you solved this multiplied by epsilon, okay, and you found that this solution was valid over a much larger region, okay? So the Taylor series was valid. This is where the Taylor series was good, but the perturbation series was good over a large region, perturbation series. Okay, that's what you discovered. So here you were doing local analysis. Perturbation theory allows you to do global analysis. So this is a local analysis. This is a more global analysis in the sense that it's valid over a large region of x. Here, we are doing local analysis again. Okay, but we're not doing local analysis near a regular point of the differential equation, but rather near a singular point of the differential equation. And we were led, there was no choice. We were just sucked into learning asymptotics. You could not avoid it. There isn't any other way of cracking into this equation. And this is what we found. We found that y of x near 0 is given not by something, you can't say what it's equal to. Doesn't work. But you can say it's asymptotic to something of the form e to the And now, what was it? 2 over the square root of x, something like that. And then there was an x to the 3/4, something like that. And then there's a sum from 0 to infinity of a sub n square root of x to the n. Okay? That was the form of the series. This series here begins a0 is 1, a1 is minus 3/16, and so on. And this is a divergent series because a sub n grows roughly like n factorial. Okay? So this is a very divergent. First of all, this is not a Taylor series because it's a series in powers of in fractional powers of x, not in integer powers of x. Secondly, it's a divergent series. So for 2 reasons, this is not a Taylor series. But it is sort of a Taylor-like series. So here you have an essential singular behavior, and then a Frobenius-like behavior, and then a Taylor-like behavior. And you notice you can peel off these behaviors. They're contributing one at a time. So you can identify the structure of this equation, okay? But all of this is only valid as x goes to 0. And there's a fantastic amount of new mathematics in that. It's really wonderful. In fact, when I teach this stuff at my university, the way I look at this stuff is I say, you know, the first really amazing thing that you came across when you started to study mathematics, the first really amazing bunch of things was the things that you learned in your calculus course, first year undergraduate mathematics, because there's a bunch of new concepts that are fantastic. I mean, it's amazing. People, you know, it's a credit to the human brain, the concepts that you come across in calculus. Absolutely fantastic. You learn the notion of a limit, which is a fantastically subtle notion. And then once you have a limit, you define a derivative, which is a very, very subtle and interesting concept. And calculus is fantastic because a whole world opens up in front of you. It's a whole new way of thinking about mathematics. And then for the next few years, it's routine. You know, you go through differential equations and you go through multivariate calculus and all this stuff. But there's nothing really shockingly new. And then you come to this stuff. And once again, there are a whole bunch of new concepts. In particular, this symbol. This is an amazingly subtle symbol. Because this is not equal to that. Can't be, because this doesn't exist. But all the information you need about this function is in here. And using this stuff, you can calculate that function with arbitrary precision. That's amazing. That's absolutely amazing to me. Okay, so any questions about that? I mean, I think calculus is fantastic. In fact, what's the fundamental theorem of calculus? Anybody know? It is fantastic. The fundamental theorem, do you know what it says? What does the fundamental theorem of calculus say? Say it again? Yeah, it relates the integral and the what's so fundamental? What's so fantastic about that? You know, with a name like the fundamental theorem of calculus, that sounds really important, sort of. I mean, why is it such an important theorem? This is the first example of unification. I mean, you're studying, you know, advanced theoretical physics here, and you're studying the physicists, you know, have this urge to construct a unified theory, right? Unify all these different branches of physics, and the first example of unification in physics was the notion that that the theory of electricity and the theory of magnetism are really the same theory. You know, there were all these experiments on electricity and all these experiments on magnetism, And people thought they were two completely different phenomena. Then they realized, no, they're the same phenomena. The reason that the fundamental theorem of calculus is so fantastic is that there are two theories of calculus that have nothing to do with one another. The first is the theory of the derivative, right? And the derivative is defined as a limit. You know, you do something like y of x plus epsilon minus y of x divided by epsilon, and then you take a limit as epsilon goes to 0, and you construct a derivative, and you play with that, and you do things with that, and that's fine. And then later on, you're interested in calculus, and this tells you something about when a curve reaches a maximum and stuff like that, okay? And then later on, you define an integral, which has nothing to do with the derivative, okay? An integral is a way of calculating an area under a curve, and the way you do that is you draw some curve, and then you say, I introduce a lattice here, lattice of points, a net, okay? And you calculate the area of each of these rectangles, or these trapezoids, whatever you want to call them, and then you take the limit as you make these points come as close together as possible, and this distance here, epsilon, goes to 0, and you've got a way of calculating the area under a curve. So you've done two separate things in mathematics that have nothing to do with one another. These are two theories. This is the theory of differential calculus. That's the theory of integral calculus. So what? Okay. Then along comes the fundamental theorem, and they're the same theory. Wow, that's amazing. That's unification. Okay, it's a perfect example of unification. All right, anyway, all of those amazing concepts end, I think, after the first year of undergraduate mathematics. And then, when you're doing graduate work, things like this come along. And boy, there's a whole bunch of spectacular new concepts. Okay, so now you found this series, and you can see that the series actually approximates the function. That's what this picture shows you. So if I take the exact function and I divide it by the very first term, just this x to the 3/4 and e to the e to the 2 over the square root of x, and I let x tend to 0, you can see that this approaches a constant. And it's roughly constant, from about 1/2 down or something, or even from 1 all the way down to 0. So 1 is pretty darn close to 0 here. Okay? So that's very impressive. And when you take two terms in the series, you get something like that. And you can see this is approaching a constant even better. Okay? So how do you extract information from this divergent series? Well, let me just raise this up a little bit. If you're calculating a function and you have an asymptotic series that represents this function, okay, so this series is asymptotic to f of x as x goes to 0. Again, what does this mean? It means, so there's sort of a reason why we use that sum sign. The reason is that a sequence of partial sums is each term in the sequence of partial sums becomes a better and better approximation to f as x goes to 0. Not as n goes to infinity, but rather as x goes to 0. Okay? So what this means is that for all n, it is true that f of x minus the sum from n equals 0 to n, a sub n x to the n, is asymptotic to a sub n plus 1, x to the n plus 1, as x goes to 0. Okay? So let's ask, suppose you know that this is true, how do you use that? You use that to construct the optimal okay, and if you ask most physicists, many physicists don't know Padé theory at all, but they are sort of aware of the optimal asymptotic approximation, and this is the most naive thing you can do with an asymptotic series. So suppose you've calculated this the coefficients in that asymptotic series. How do you use it? Well, you argue that even though this series diverges, it can give you a pretty good approximation to the function f of x. So why is that? So typically, if this is n, and you make a plot of this term here, an plus 1, x to the n plus 1. So for a particular value of x, fix x, and make a plot of this term as a function of n, typically what you see is that the terms in the series get smaller for a while, okay? But this is typically a divergent series. So eventually they turn around and blow up. That's, this is the normal way an asymptotic series behaves. But you understand that this term here is a measure of the error. It's not exactly equal to the error, but it's asymptotic to the error. Okay, so if you ask, how close does the nth partial sum come to the function you're trying to calculate, it comes approximately that close. It becomes exactly that close as x goes to 0, but when x is small, it comes approximately that close. So this is a measure, of the error in the asymptotic approximation. This is a measure of the error. Okay? So therefore, if you're trying to calculate this function f of x for a particular value of x, okay, I haven't said which value of x, but some value of x, 0.1 or something like that, then what you do is you make a plot of these terms here and you say, that guy is the smallest guy. Therefore, we expect that if you take this partial sum will have the smallest error. And that's called the optimal asymptotic approximation. Okay? So the first, historically, the first really impressive use of asymptotic series was given a Nobel Prize, Schwinger and Feynman and Tamanaga got the Nobel Prize when they calculated G minus 2 in electrodynamics. And they were very, very lucky because what they had was a series in powers of alpha, sum of a sub n alpha to the n in electrodynamics, where alpha is equal to this famous number, 1 over 137, okay? And the series that they were calculating using Feynman diagrams is a divergent series. But fortunately, they were able to use, fortunately, the first few terms in the series were very small. And so they got a very good numerical answer. But they didn't do Padé. They didn't try to do Padé. In fact, nobody knew anything about Padé. Okay, so the use of Padé in calculating, combining it with Feynman diagrams and Feynman series came later on. Yeah?
So if I compute anything in renormalized QED, would it always be the same that it would have this form?
In fact, yes, it's a divergent series.
No, so, what I'm saying is that, you said Feynman, Tamanaga, and Schwinger were lucky. But what if they didn't compute G minus 2, but something else in QED?
Oh, it's still, alpha is still in QED, it's still 1 over 137. Right. Okay, so typically that's, so you get, maybe, nobody really knows how rapidly the series is going to grow. It's very likely growing like, it may be growing like n over 2 factorial, but nobody knows. In four-dimensional QED, nobody knows for sure what the large order behavior of the coefficients is. That's an open problem. Okay, in phi to the 4 theory, less than 4 dimensions, it's known. Okay, but in QED, it's not. Kind of interesting. Be a beautiful problem, by the way. Very interested in a problem like that. Be a really interesting problem to work on. Maybe if we have time, I will show you that the large order behavior of the coefficients in the Feynman perturbation series is related to the vacuum, the lifetime of the vacuum in the unstable version of the theory. That's an amazing result. If you have a phi to the 4 theory, if you have a G phi to the 4 theory, okay, the potential looks like this, okay? And if your Lagrangian has a potential of the form m squared phi squared plus G phi to the 4, that's in a phi to the 4 field theory, the potential looks like this, okay? Consider an m squared over 2 phi squared minus G phi to the 4 theory. This theory looks like this. So if you put a state in here, so this is the physical theory that we're looking at. And there are states in this potential well. And in particular, the lowest state is the ground state, and it's stable, as you can see. In this theory, the corresponding state is unstable because it can tunnel through here. Okay? And this is essentially Hawking radiation, tunneling out of a black hole, going out to infinity. Okay? And if you calculate the lifetime of the state in this theory and take its nth inverse moment, that will give you the large order behavior of the coefficients in the perturbation expansion. I can prove that to you. It takes about half an hour. Very interesting result. But that calculation is very hard to do in electrodynamics. Very interesting. Okay? But that's where the physics is. So the lifetime of the state determines the large order behavior of perturbation theory. And it tells you how rapidly the perturbation series diverges. Okay, so this is the optimal asymptotic approximation. But you understand that this is very frustrating. Because suppose you're really strong, okay? And you've been able to calculate all of these coefficients. You've been able to calculate all the way up to 10th order in perturbation theory, okay? But the optimal asymptotic approximation is here. Do you get any reward for calculating these terms? No, because if you merely try to add up the asymptotic series, the answer gets worse and worse and worse and worse, because this is a measure of the error. So the error is getting bigger and bigger and bigger. Disgusting. It's horrible. That's why we do PADE, because PADE is not concerned about the fact that these numbers are getting bigger and bigger. The PADE continues to converge. That's the reason why we learn PADE theory. It's much, much better than the optimal asymptotic approximation. Okay, so I hope the mathematics is beginning to fit together now in your mind. Let me give you a very brief illustration, because I think this is a very cute example. This is one of the very nice, just lots of nice memories I have about quickly solving problems using asymptotics. I was in my office, this is many years ago, and another theoretical physicist walked into my office. He was working on condensed matter, and he was doing a calculation involving the Kondo effect. It's not important what the calculation was, but he had come up with a series of the form if you eliminate all the dimensional constants and so on, when you boil it down, he had a series of the form x to the n over n factorial squared. Okay, that's a rapidly convergent Taylor series. Okay, but what he needed to know was the answer to this question. How does f of x behave as x goes to infinity? And he didn't know. And and he was trying to sum up the Taylor series for large values of x, which of course is not going to do very much. So he said, is there a quick way to understand how f of x behaves for very large values of x? The answer is, once you know asymptotics, you can crack problems like this in a second. It's fantastic. So let me just show you a quick solution to the problem. So how does f of x behave? Let's find the differential equation that f of x satisfies. Okay? So f prime of x is the sum from n equals 1 to infinity, not 0, because the derivative of this first term in this series is 1. X to the n minus 1 over n factorial n minus 1 factorial. You agree? Okay, take a derivative. One of the n factorials turns into an n minus 1 factorial. Okay, now let's multiply back by x. Okay, x f prime is the sum from n equals 1 to infinity x to the n over n factorial n minus 1 factorial. And now let's take another derivative. X f prime prime would be the sum from 1 to infinity x to the n minus 1 over n minus 1 factorial times n minus 1 factorial. And if we shift the index, right, if we raise n, replace n by, if we just send n goes into n plus 1, we have to compensate by lowering the limit to 0. That gives us the sum from n equals 0 to infinity x to the n over n factorial n factorial. Ah, that's just f of x. Okay? So f of x satisfies the differential equation f prime prime, take the derivative here, times x, plus f prime is equal to f. So what we need to know is, what is the behavior of the solution to this equation as x goes to infinity? But x equals infinity is an irregular singular point. So therefore, we would like to try a solution of the form, we would like to do what Mr. Green told us to do. We'll make a substitution, f of x is equal to e to the s. Okay? And we'll plug it into this equation. So over here is an x times s prime prime plus s prime squared. Okay? And then there's an f prime, which is s prime, and then there's an f. So that's the equation. Now, this is an equality, and it's a horrible equation, and we can't solve this equation. However, we know that we expect that s double prime will be negligible compared with s prime squared as x goes to infinity. That's what we expect. Okay? So therefore, I could take this horrible equation, which is a second-order equation, and replace it by an asymptotic relation and neglect that term. Okay? So now it reads x times s prime squared plus s prime is asymptotic to 1 as x goes to infinity. Okay, Now this is a quadratic, this is an easy equation. Yeah? Because we are at an irregular singular point, and we argued, remember, that oh no, it doesn't matter what x is going to. This is if you have an irregular singular point at x equals anything at all, we expect that this will be small compared with that. Okay, if x is going to, if x is going, in this case, a happens to be infinity, it doesn't matter which point it is, okay, we expect that at infinity, we're going to have a behavior something like, we expect f to behave something like e to some constant times x to some power p. And infinity, this is an infinity, p is going to be positive. So it's going to be blowing up. Okay, that's what we expect. Okay, and that's the kind of singular behavior we expect. If you now calculate s prime prime, and you compare it with s prime squared, s prime prime will be negligible compared with s prime squared. Okay? So we have an equation like this. Now, this is a really hard equation to solve because it's a quadratic equation, right? Squared plus is 1. So we have to remember the quadratic formula. Can you remember the quadratic formula? Nah. That's kid stuff. I don't remember the quadratic formula. The point is we're trying to solve this asymptotic relation, and who needs the quadratic formula? All we need to do is the method of dominant balance. Okay? So we have to ask, which is the important term here? Okay? So for example, is this the important term? Suppose we throw this term away. What if we throw this term away? Okay, maybe this term is unimportant compared with this and this. If you throw this term away, if you say x s prime squared is negligible, if you throw that term away, then there's a balance between s prime and 1. So that says s prime is of order 1. But if s prime is of order 1, and it's multiplied by x, then as x goes to infinity, this is blowing up, and this is only of order 1. Wrong. That can't be right. So this cannot be the small term. This must be a big term. Okay? Now, what if this term and this term balance? What if we throw away 1? Okay? Maybe 1 is the small term, and we want to keep this and this term. Then we conclude that x s prime squared, it would be asymptotic to minus s prime. Divide by s prime, so you conclude that x s prime is asymptotic to minus 1. So s prime is asymptotic to 1 over x. Well, wait a minute. What did we do here? If s prime is asymptotic to 1 over x, it's small. That's a small term. It's of order 1 over x. But we threw away 1 compared with 1 over x. Nope, that's no good. So there's only one other possibility. We have to throw away the s prime term. Okay? So this is the first possibility, no good. This is the second possibility, no good. Third possibility, we throw away s prime. Suppose we throw away s prime, and we keep these terms. X s prime squared is asymptotic to 1. Then we would conclude that s prime squared would be asymptotic to 1 over x. Right? So s prime would be asymptotic to plus or minus 1 over the square root of x. Is that consistent? You think that's consistent? Well, if we're concluding that S prime is of order 1 over the square root of x, and we're throwing away S prime, this guy is of order 1 over the square root of x, compared with 1. Can you throw away that term? Yes. That's consistent. Good. Look at that. We got the answer, and we never used the quadratic formula. We don't need the quadratic formula anymore. So we have two solutions. There's S prime. And we conclude that S is the integral of this, right, which would be plus or minus 2 square root of x plus a constant. Who needs a constant? Constant is negligible compared with x as x goes to infinity. So we know the controlling factor of the asymptotic behavior. We know already that this function is growing something like e to the plus 2 square root of x as x goes to infinity. That's very interesting. But that's not the asymptotic behavior. You have a question? Yeah.
Why is x regular singular form?
Yeah. So you know how to classify a point in the finite plane, right? You just ask, is there a Taylor series? How do you classify the point at infinity? Easy. Map the point at infinity into the point at 0. So make a change of variables. Just say let x equal 1 over t. Find the differential equation not in x but in t, and classify the point at 0.
So you
Okay?
change the
And
derivatives.
since this is, since this equation, I invite you to do that, okay, just to check it out. But you'll find that t equals 0, the coefficient functions of the equation at t equals 0 do not have Taylor series. Okay, that's how you classify the points. But that's a very good question. Okay, so we're not done yet, right? What we know is that this function is going to behave like e to the 2 times the square root of x, something like that. But we're not done, because we can't say, we don't have the right, we do not have the right to exponentiate this asymptotic relation. Just because s is asymptotic to plus or minus 2 square root of x, we cannot conclude that f is asymptotic to e to the plus or minus 2 square root of x. By the way, how do I know that it's the plus sign that's relevant and not the minus sign? Because the minus sign says it's going to 0 exponentially, but this is the Taylor series. This is not going to 0. This is monotone. All the terms are positive. So this function is a monotone increasing function of x. So it can't be asymptotic to e to the minus 2x. It must be e to the plus. E to the plus 2 square root of x. Okay. So the last part of the analysis is easy. Let's do it. So what do we do next? We say, suppose we are looking for this function s. We know that s is going to be equal to 2 square root of x plus a correction term plus c of x. Notice this is inequality. So we're jumping back and forth between equal signs and asymptotic signs very, very carefully. Okay? So we say, let s equal this, but we know that s is asymptotic to that. Therefore, c is negligible compared with square root of x. We expect c of x to be negligible compared with square root of x as x goes to infinity. And furthermore, c prime should be negligible compared with 1 over the square root of x as x goes to infinity. And c double prime should be negligible compared with 1 over x to the 3/2 as x goes to infinity. Okay? Great. So if s is this, s prime is equal to 1 over the square root of x plus c prime. S double prime is equal to minus 1 over x to the 3/2 with a factor of 2 here. plus c double prime. All of these are equalities, okay? And the equation, the equation that we're trying to solve is this equation right here. So let's substitute this stuff into this equation. Got it? You see the calculation? So the first term is x times, now, there's an s double prime, which we said is minus 1 over 2 x to the 3 halves plus c double prime. Then there's an s prime squared, so we have to square that guy, plus 1 over x, and the square of that is c prime squared, and the cross term is plus 2 over the square root of x c prime. So that's this piece. Then there's an s prime, and s prime is 1 over the square root of x plus c prime, and that is all equal to 1. So we have a disgusting, messy equation. But one good thing happens, you can see. You notice that x times 1 over x is 1, and that guy cancels that 1. And that's the check that the first term in our asymptotic expansion is correct. Okay? So we're always going to see one cancellation. Good, so there are not that many terms left in the equation, but it's still pretty messy. Okay? So let's write down all the terms. We have minus 1 over 2 x to the 3 halves plus c double prime plus c prime squared plus 2 over the square root of x c prime. Okay, those are all the terms in this square bracket. And now I'm going to divide the rest of the equation by x. Okay, so there's a 1 over x to the 3 halves and a c prime over x, and all that is equal to 0. Okay? Okay, great. Horrible equation. However, we are assuming that c double prime is negligible compared with this. And I see in this equation is c double prime. There it is. And I also see a 1 over x to the 3 halves. So we'll just throw this away. We expect this guy to be negligible. Great. Now it's not a second-order equation anymore. It's only a first-order equation. But it's still nonlinear. Okay? However, we see that c prime is negligible compared with 1 over the square root of x. This is c prime times c prime. This is c prime times 1 over the square root of x. Which is more important? That term. That must be more important. So we throw away that term. Great. Now it's not only a first-order equation, it's a linear first-order equation. Okay? Now let's keep going. This is c prime over the square root of x, and x is going to infinity. This is c prime over x, which is more important. This is c prime divided by the square root of x. This is c prime divided by x. X is much bigger than the square root of x as x goes to infinity. Throw it away. Great. Okay. Oh, there's a little more. This term combines with that term, doesn't it? Okay, so I can erase that term. This is minus 1/2, and just insert a 2 over here. Oh, wait a minute. Almost everything is gone. This is really great. All that I'm left with is an equation that says 2 over the square root of x times c prime is asymptotic to minus 1 over 2x to the 3 halves. That's the equation that we have to solve. So c prime is asymptotic to minus 1 over 4 x. That's all. So c is asymptotic to minus 1/4 log of x. Great. Okay, so now we know, let's put it over here. So since f is equal to e to the s, we now know that S is asymptotic to 2 square root of x minus 1/4 log of x minus 1/4 log of x plus more terms. But these terms, I'm not going to go through the calculation, are small compared with 1, and therefore it is now valid, I haven't shown you that, but it's true, it is now valid to exponentiate this and to conclude that e to the s is asymptotic to e to the 2 square root of x, and the exponential of this is x to the minus 1/4 times some constant times a series in powers of 1 over x at infinity. Forget the series. Let's just forget the series. Just, who cares? We won't even worry about that. These would give us really accurate approximations to this function f. But let's ask the following question. Suppose we just forget this series. Suppose we just study this simple asymptotic approximation. How accurate is it? Okay, the question is, we are claiming that f of x is asymptotic to e to the 2 square root of x, x to the minus 1/4, times some constant as x goes to infinity. How accurate do you think that is? Look how simple that approximation is. Just an exponential and a power. How accurate do you think it is? Okay? So let's make a plot. Let's compare the original Taylor series representation of the function with this trivial, I mean, look how long it took us to calculate this. This is trivial. Just bang, just like that. Let's compare that with this. And let's see whether or not this is an accurate approximation. Now, there's only one thing that I'm leaving out here. I have not told you how to calculate this constant. And this constant, is very interesting, involves the square root of pi. Okay? But by looking at this differential equation, this differential equation here is a linear equation, so it cannot determine that constant. So we know that there is some constant here, but we don't know what that constant is. The series knows that constant, but the differential equation doesn't. Okay? Do you understand how... Okay, let's say, how would we determine this constant? Well, we know from this series representation that f of 0 is equal to 1. Can we incorporate this fact into here? No, not directly. Why? Because this is local analysis as x goes to infinity. And infinity is too far away from 0 to use this piece of information directly. Yeah. Sorry, how is it?
I mean, it's not clear to me. F of 0 is 1.
Just plug in 0.
But then we have 0 to the power of 0, and it's undefined.
No, from here. Just plug in x equals 0. This is the definition, if you like, of the function f of x. Okay? If I plug in x equals 0 here, then I just get f of 0 equals 1. Everything vanishes
First
except
the series is 1. And then you said x equals 0.
Yeah, but that's not plugging in 0 and...
No, so you pull out the first term in the series and then have all the other ones.
this is a convergent series.
Yeah, that's true.
This is wildly convergent. This is not just an n
He's
factorial.
unhappy about the fact that you can have 0 to the power 0.
I mean, the first term would be 0 to the power of 0. So it's
X to the n?
Yeah.
But you have a 0 to the 0 is 1. Do you agree to that?
I'm not sure.
The limit as x goes to 0 of x to the x is 0. This is 1. Right? 0 to the 0 is 1.
But
Yeah?
it could be some, I mean...
No, but just right. I'm not sure what the problem is. This is a polynomial. This is a polynomial here, right? This is a polynomial. The first term in the polynomial is 1. plus x over 1 factorial squared plus x squared over 2 factorial squared plus x cubed over 3 factorial squared, and so on. This is just a polynomial in x. So plug in x equals 0, that vanishes, da, da, da. Okay? Okay, so the question is, can we use this information? No, we can't. We don't know how to do that. Because this is non-local information. We have only solved this equation here at infinity. And we don't know how to incorporate this fact. So incorporating this fact involves non-local analysis, which is what I'm going to be showing you for the rest of this course. But for now, we're concentrating on local analysis. So we don't know how to determine that constant. But we do know how the function behaves. So this is what I'm going to do. And you're going to be impressed. Okay? Let's do the following. First of all, let's calculate the exact function f of x. This is the exact function. Okay? And let's plot two things. The first thing is, let's make a plot of the sum from n equals 0 to 10. That's 10 terms in the Taylor series. X to the 10 over n factorial squared. And the second thing we will do is we will plot e to the 2 square root of x times x to the minus 1/4. And to see which is a better approximation to f exact, we will divide this by f of x exact, the exact function, and we'll divide this by f of x, exact function. Okay? Now, if this is a good approximation to f, the ratio should be, this ratio, if it's good, okay, if this is good, this should be 1, of course. But if it's not a good approximation, then this should be 0. Right? So now let's see what happens. Okay. So, okay. So, first of all, I want you to look at this curve right here. This curve right here is the first 10 terms in the Taylor series divided by the function f of x. Here I'm calling it y of x. Okay? And notice that this ratio at 0 is exactly 1. That's because the Taylor series is perfect right at x equals 0. And the Taylor series remains equal to 1 for a very long way. Taylor series is very good. But eventually, the Taylor series falls off, this ratio of the Taylor series divided by the exact function, it falls off. This is too clumsy. Let's get a pointer. Okay. Notice this ratio goes to 0, and it's terrible from there on. Okay. Now this is a logarithmic scale, so this is a 1,000th, and a 100th, and a 10th, 1, 10, 100. By the time you get up to 100, the Taylor series is getting terrible, and it's lousy when you're beyond 100. So all the way from 0 up to 100, the Taylor series is fabulous. It's great. You can be very happy with it. Beyond 100, the Taylor series, even though the radius of convergence of the Taylor series is, what is it? It's infinity, of course. But even though the Taylor series has an infinite radius of convergence, it stinks. It's very, very bad. Why is that? Because this is a polynomial, this thing here is a polynomial of degree 10. How rapidly does a polynomial of degree 10 grow? It grows like x to the 10. Can't grow any faster than that. But the actual function that we are calculating here is growing like an exponential. It's growing like e to the 2 times the square root of x. So the Taylor series simply cannot keep up with the function. You can't approximate something growing like e to the x by a polynomial of finite degree. If you're going to make x bigger and bigger, you've got to take more and more terms in the polynomial. You have to. Polynomial can never keep up with an exponential growth. However, let's look. So here, the Taylor series is good, and then it's terrible, just really terrible. Okay? Now, the constant, this constant out front, the c that I wrote down, turns out to be 1 over 2 times the square root of pi. This is really an interesting result. And square root of pi occurs very often in asymptotic approximations. And I'm not going to explain to you where that's coming from, not right now. But here is the constant, okay? But here is the x to the minus 1/4 e to the 2 square root of x. Let's look at that ratio. Well, of course, at infinity, it's perfect. It's 1. Now, this calculation is only valid as x goes to infinity, right? We did local analysis at infinity. But is it good at 1,000? Is 1,000 close enough to infinity? You bet it is. This answer is 1. How about at 100? The answer is 1. How about at 10? The answer is only a few percent away from 1. How about at 1? The answer is only a few percent away from 1. How about at a tenth? The answer is, well, not very far away from 1. It's only about 15% off. And this is only, you understand, this is only one term in the asymptotic series, the very first term. So we gave the Taylor series some unfair advantage. We allowed the Taylor series to have 11 terms in it. And we only took one term in the asymptotic series. And I want you to notice that the asymptotic approximation is pretty darn good all the way down to about 100th. So 0.01 is pretty close to infinity. You understand, all of this analysis was valid at infinity. When you actually look at the numbers, the asymptotic analysis is unbelievably accurate. And we haven't even tried to do an optimal asymptotic approximation or a PADE. Why not? Because if I took a few terms in the series, which I haven't calculated for you, but if I took a few terms and I PADE'd them, it would be so good that it would be an unfair race. It's simply totally unfair, a comparison between a Taylor series and a asymptotic series. So even though this is a fantastically rapidly convergent series, this is not n factorial. This is n factorial squared. Boy, is that a convergent series. This series is terrible compared with one term in a lousy asymptotic approximation. And we have to understand, why is it that the divergent series is so incredibly good? Okay, and we're going to talk about that. We have just enough time to talk about it. Okay, so any questions so far? I want to show you one more example of how good asymptotics is. This here. I'm going to show you, we're going to be talking about WKB in detail, and there's one function that we need to discuss, and it is defined by this very, very famous differential equation. Anybody know the name of that differential equation? It's a really, really important differential equation. Yeah. Very good. Excellent. Excellent. Okay. So this is Airy's equation. Nice name, isn't it? How'd you like to be called Mr. Airy? It's better than being called Mr. Snodgrass or something like that. Bahaskus Guggenfatzel or something like that. Okay, so this is his equation. And believe it or not, the solution, there are two, of course, this is a second order equation. And there are two solutions to this equation, two linearly independent solutions. One solution is called an Airy function. Okay? And it's written ai of x. Okay? And the other solution, I wish they had called it hi of x, which is a hairy function. Okay? But they didn't. They called it bi of x, because b comes after a. So it's traditional to call it bi. So that's a Berry function. Okay? Airy and Berry. Okay? And these are the two linearly independent solutions to this equation. Okay? And this solution here, these two solutions are distinct, quite distinct. If we wanted to know how these solutions behave as x goes to infinity, okay, how do these solutions behave? We can now write down the answer now in a second. Okay, now there's one, I hate memorizing formulas, but there's one formula that's really, really important, and that's the WKB formula. So do you remember that if you have a differential equation of the form of Schrodinger type, y prime prime equals q of x times y, as at an irregular singular point, in this case as x goes to infinity, q of x goes to infinity, so we have an irregular singular point at infinity. You know that y of x is asymptotic to q to the minus 1/4 times e to the integral of the square root of q. Okay? And there's a plus or minus sign. Okay, and there's some constant here, and we derived this last time. Okay? So how do solutions to this equation behave? All we need to do is to plug into this formula. It takes 1 second, and what we know is that the solutions to that equation, y of x, behave like e to the plus or minus. Now, how does this, what is this? The q in this case is just x. So the square root of q is the square root of x. So the integral of the square root of x is 2/3 x to the 3/2 power. And q to the minus 1/4 would be x to the 1/4. And there's some constant. And this is how the solutions to the area equation behave as x goes to infinity. Bang! Are we fast? Isn't that impressive? Okay? I mean, if you really want to be impressive, call up your mom, okay, and say to her, consider this equation, y prime prime equals x to the times y, okay, and say to your mom, give me a number. Okay, so your mom tells you her favorite number, 7. Okay, terrific. You say to your mom, I know how solutions to this equation behave. They behave like a constant, asymptotically, as x goes to infinity. They behave like a constant times x to the minus 7/4 times the exponential of the integral of the square root of this. The integral of x to the 7/2 is x to the 9/2 times 2/9. And as x goes to infinity, that's the way the solutions behave. She'll say, how did you know that? So, just learned a lot at the perimeter. You know, I can just do this in my head. Just plug. Very impressive. All right, so this is how the solutions behave. In fact, the Airy function behaves like e to the minus 2/3 x to the 3/2. That's the minus sign over x to the 1/4, and the constant out front is 1 over 2 square root of pi. In fact, you can regard this as a definition of ai of x. This is how ai of x is normalized, if you like. Okay? And bi of x behaves like 1 over the square root of x, not 2, 1, times e to the plus 2/3 x to the 3/2 over the square root of x. Okay, so bi grows at infinity, ai decays. This is as x goes to plus infinity. Oh, sorry, not x, square root of pi. Square root of pi, not x, pi. Nope. Crap. Fourth, okay? Right, so these are the two asymptotic behaviors, okay? And the coefficient, you can think of this as the definition of the Airy function. That, in some sense, can be used to define it. Okay, so question is, you think this is an accurate approximation? Let's take a look. So here, where did I put here? There it is. Okay. So if you put that differential equation on a computer and you integrate it and you plot the Airy function, here is ai of x right there. Okay? And ai of x has some value at x equals 0, some numerical value. Okay, it's some transcendental number, and it comes down like this, and it goes to 0. And the Airy function is a higher transcendental function. There's no simple formula for it in terms of exponentials and sines and cosines and whatever. There's no simple formula for it. You just have to give it a name, ai of x. Okay? But here is our simple asymptotic approximation. It's simple and elegant, and you can do things with it. You can't differentiate ai of x. The derivative is ai prime of x. Can't do anything. But if you really want to differentiate it and find its slope, for example, you can differentiate this. That's a simple elementary function of x. You can do it. Okay? And this is this asymptotic approximation, and look how accurate it is. And you can't see the difference between those two lines when x is 2. Now remember, this was asymptotic analysis as x goes to infinity. That's local analysis at x equals infinity. But already 2 is so close to infinity that you can't see the difference between the two curves. And we haven't included the additional terms in the asymptotic series. Remember, if you wanted to calculate the Airy function with arbitrary precision, this asymptotic approximation is followed by a series, a sub n, in inverse powers of x. Not actually powers of x, but x to the 3/2, it turns out. But that doesn't matter. We haven't attempted to pade this series to get a really accurate approximation. We're not even bothering to include that series. We're just terminating the series at the first term whose value is 1. So just forget that series. Just forget it. Look already how accurate the approximation is. So why is it that an asymptotic approximation is so incredibly accurate? There's a reason. And it's really interesting, and I'm going to give you a hint at the reason. And it has to do, it's a fancy word. It's called the Stokes phenomenon. That's a very fancy word. And I'm going to try to explain to you why it is that asymptotic series are so good. Okay? And we're going to then make use of that fact in what we do from here on. Okay, so let's fix that up. So why is it that asymptotic series are so good? Okay? Until now, we have been sloppy. Okay? We have said that we are doing asymptotics as x goes to infinity, but we haven't said in what direction. Okay? Remember, x in principle is a complex number, and when you say x is going to infinity, you mean going to infinity in the complex plane. Okay? So you mean x is getting very far away from the origin, say out here somewhere. So are we going to plus infinity, or are we going to absolute infinity, or, you know, is it absolute x that's going off to infinity? Is the distance to infinity getting large? Or what is it exactly that's getting large? Okay, and that's an interesting question. In fact, it's an amazingly deep and fascinating question. And here's the answer. Okay? Suppose I said to you, can you find an asymptotic approximation to sinh of x? What is sinh of x asymptotic to as x goes to, first, as x goes to plus infinity? Just to plus infinity along the real axis to more and more positive values. Can you find an asymptotic approximation to sinh of x? What would it be? E to the power, who's saying? E to the x over 2. Right. So, very good. Why is that? Because remember the definition of sinh of x. This is defined as 1/2 times e to the x minus e to the minus x. Okay? That's the formula for sinh of x. So as x goes to plus infinity, this guy becomes just negligible. You can just throw it away compared with that guy, right? So sinh of x is asymptotic to 1/2 e to the x. Okay? On the other hand, as x goes to minus infinity, how does sinh of x behave? You got a minus sign. This formula changed. Wait a minute. Minus. Are you telling me that there are two different asymptotic approximations depending on how you go to infinity? You notice here there's no minus sign. Here there's minus sign. Ooh. That's very interesting. So what is happening in the complex plane? If you look at, this is the complex x-plane, as you go to infinity this way, we know that the asymptotic approximation is this one. This is the number 1. This is number 1 here. So asymptotic approximation number 1 is valid here. If you go to infinity in this direction, number 1 is still valid. Where does it stop being valid? Say it again? On the imaginary axis. That's right. Because on the imaginary axis, you can no longer neglect this compared with this. Right? In fact, this and this are roughly the same size. They're both of order 1 on the imaginary axis because they're both oscillating. So in fact, this asymptotic approximation number 1 is not valid in a circle in the complex plane. It is only valid in a wedge called a Stokes wedge, and the opening angle of the Stokes wedge is pi. Okay? This asymptotic approximation ceases to be valid as soon as you get to the imaginary axis. It's no longer valid here. So the correct way to write down this asymptotic approximation is this. So now I'm going to give you, finally, I've been concealing something from you. This is valid as absolute x goes to infinity, where the argument of x is less than pi. Finally, I have written down a correct asymptotic approximation. Or this is less than, argument of x is, we'll call it less than pi over 2. Okay, up to plus pi over 2 and down to minus pi over 2. Okay, so the total opening angle is between, so let's maybe it be more clear if we wrote it. Argument of x is less than pi over 2 and greater greater than minus pi over 2, between minus 90 degrees and plus 90 degrees. This is how you go to infinity. You can only go to infinity in that wedge. This asymptotic approximation here, this is not the correct way to write it down. The correct way to write it down is as absolute x goes to infinity, but the argument of x has to be bigger here than, let's call this point here minus pi, and this is minus 3 pi over 2, okay? So it has to be bigger than, or we can call this pi, we'll call this 3 pi over 2, go around here, okay? So it has to be bigger than pi over 2, but it has to be smaller than 3 pi over 2. Okay? So there's, again, a wedge. So in fact, to find an asymptotic approximation to a function, typically that asymptotic approximation is not valid as you go to infinity in all directions in the complex plane. Okay? You generally need several different, here we need at least 2 different asymptotic approximations to approximate sinh of x for all arguments in all directions in the complex plane. So here is the conclusion of this lecture. Why is it that asymptotic approximations are so incredibly good like this? Because you don't ask that much of an asymptotic approximation. That's why. So what am I talking about? Okay? What am I talking about? Well, you see, a Taylor series, if it converges, converges in an entire circle. Taylor series are terrible because they have to approximate the function in all directions. So this Taylor series here, for example, this Taylor series has to converge for all x everywhere in a circle in the complex plane. And in this case, the circle has an infinite radius of convergence. But Taylor series, they either diverge, in which case they're divergent series, so they're not Taylor series, or else they converge, but when they converge in all directions. An asymptotic approximation doesn't converge in all directions, and in fact, the asymptotic approximation that we derived, namely this one, is only valid in the cut plane. This asymptotic approximation is valid all the way up to here and all the way up to here, but it's not valid on the negative axis. So you don't ask as much of an asymptotic approximation as you do of a Taylor series. That's why the asymptotic approximation is so good, because it doesn't have to be valid in all directions, in angles all the way from 0 to 2 pi. Okay, it's only valid in a wedge. Therefore, in its wedge, it can be fantastically accurate. So, to be specific, this asymptotic approximation that we wrote down for the Airy function that I'm showing you here, okay, let's bring it down. Okay, this asymptotic approximation for the Airy function is only valid in a wedge that looks like this. This is the wedge. Okay, so it goes out to 120 degrees in this direction and minus 120 degrees in that direction, but it doesn't cover the entire complex plane. This is the wedge in which this is the correct asymptotic approximation for the Airy function. That's why it's so good, because you don't ask as much of an asymptotic approximation. Okay, now this is what we have to talk about next time, but let me just summarize by saying this is an analytic function. This is an analytic function. Okay? But the analytic continuation of an asymptotic approximation does not agree with the asymptotic approximation of the analytic continuation. Okay? If you analytically continue AI of x, and you analytically continue its asymptotic approximation around and around and around, all of a sudden when you get to 120 degrees, they stop being, the asymptotic approximation fails. Okay? That's great news, because it means that the asymptotic approximation doesn't have to agree with the function that it's representing everywhere, only in some angle here. And at a certain point, it cuts out. It stops being valid. Just the way the approximation to sinh of x stopped being valid at 90 degrees. Okay? And that's called the Stokes phenomenon, and that's the reason, that's the very deep reason why the magic of asymptotics works. It's because asymptotic approximations don't have to do as much as, say, a Taylor series approximation. Taylor series have to be valid in all directions. Asymptotic series only have to be valid in some wedge. Of course, it's a different wedge for each function, and typically the wedge is like 90 degrees or 180 degrees, maybe all the way up to the negative axis, but eventually it stops being good. Okay? That's the power of asymptotics. You don't ask an asymptotic approximation to do as much for you. Okay, any questions about that? This is just something to ruminate over and think about that tonight. And then next time I'm going to try to explain to you why asymptotic series work for actual physical problems. I'm going to summarize some of the theory behind asymptotic series. Yeah?
So if you see the Stokes wedge for Airy, what do we have?
How do we know that? How do we know that the Stokes wedge is there?
Do we have
We're going to talk
more
about
term? Okay.
that. We have to talk about. Okay. What is happening is that when you get out to an angle of 120 degrees, this stops. This begins to be. There's a changeover. Something happens to this power, which we need to talk about. Okay. So at first it's going to 0. And then it's getting big, and then it's oscillatory, and so on. And we have to trace what is happening in the complex plane as a function of the angle. And you'll see that suddenly AI of x is no longer the small function, and BI of x is the big function. And when this Stokes phenomenon occurs, it abruptly occurs at some angle. This is a really great approximation to AI of x all the way up to some angle. Okay, and then cuts out. We have to talk about that. Okay? And we're going to talk about that. Yeah.
Reminiscent of coordinate patches in general red.
I'm sorry, it's
kind of reminiscent of some coordinate patches in general red.
patches. Yeah. And you can think of this as a kind of patch. Okay? And what we're doing is we're patching in theta in the angle. Okay, so we're looking at different angles. So we're going to talk about AI, and we're going to talk about when it's good and when it's bad and when the approximation is an accurate approximation. So, okay? Yes, your question.
Sorry, I didn't understand why it's valid in a wedge related to it is so good approximation.
Oh, because you see, if a Taylor series diverges, superficially, we say it's useless. Okay? If the Taylor series converges, it's useful. But when a Taylor series, again, when a Taylor series converges, it always converges in a circle. Always. It diverges outside of the circle. It converges inside of the circle. Super. This is great. Okay? But a function can behave very differently in a circle. Very, very, very differently. For example, it might be blowing up over here, and it might be oscillating over here. If you look, for example, at a gamma function, gamma of x, how does gamma of x behave? Gamma of x, if you plot gamma of x, here's gamma of x, the factorial function. Gamma of x looks like this. And over here, it's behaving roughly like x to the x, e to the minus x. So it's growing very, very rapidly. But how does it behave over here? Okay, it behaves like this. It grows up, and then it comes up like this, and it goes down, it comes like this, and it goes like this. Very, very different behavior. Now, 1 over gamma of x is an entire function. Why? Because gamma of x is never 0. So 1 over gamma of x is a nice, smooth, analytic function everywhere. It has no singularities. So it has a Taylor series of the form sum from 1 to infinity, x to the n, a sub n. But what does this Taylor series have to do? It has to represent a function. So if I now plot 1 over gamma of x, I have a function which is rapidly going to 0 here on this side, because gamma is blowing up, so 1 over gamma is rapidly going to 0. And on this side, this function is oscillatory. Okay, it's positive, it's negative over here, right? 1 over a negative function, a negative number is negative. Then it goes positive, then it goes negative, positive, negative. So it's oscillatory here. And this poor old Taylor series, think about what you're asking this Taylor series to do. It has to represent this function for all x. So it has to go to 0 very, very, very rapidly, like 1 over x to the x. Think about how fast that's going to 0. Just dying off to 0 really fast. On the other hand, it's oscillatory here. Yuck. Think of how much work this Taylor series has to do to represent that function. So if you were to use this Taylor series to calculate 1 over gamma of 1, what's gamma of 1? 1. Okay? So if you plug in x equals 1, we know this converges to 1. We know that 1 is equal, I emphasize equal because it's a Taylor series, it's equal to the sum of an. So as n goes to infinity, this will converge to 1. It has to. But I dare you to put it on your computer. As for practice, go on to Mathematica, work out this Taylor series, plug in x equals 1, and see if this is 1. If you look at the partial sums of the series, it's ridiculous. If you make a table of the nth term in the series, sum from 1 to n of an, okay? 1, 2, 3, you make a plot of these partial sums, it will look absolutely ridiculous. It'll go, 0.7, minus 5, 14. If you look at those numbers, they're converging to 1 all right, but they're taking forever to get there. Okay, that's because this poor old Taylor series is working so hard to converge to gamma of x everywhere in the complex plane. But the asymptotic series doesn't have to worry about all this junk, because the Stirling approximation, this asymptotic approximation here, is only valid in the cut plane, but not on the negative axis. Okay? So this is valid all the way up to pi, and all the way down to minus pi, but it doesn't include pi. And because we don't make this asymptotic approximation, it doesn't have to work over there, it is very nice to you, and it converges wonderfully fast. Okay? And just for fun, try calculating gamma of 2. Okay, gamma of 2, gamma of 2 is also, what is it? 1, right? So 1 over gamma of 2, try calculating 1 over gamma of 2. So plug in, 2 to the n. 2 to the n. And this should also be equal to 1. Try doing that. You will get the most ridiculous partial sums. It's guaranteed that this will approach 1. Has to, because gamma of 2 is 1. But if you look at the numbers, they're ridiculous. They will go, some of those numbers will be minus 0.1, plus 5. It goes all over the place. Do it. Okay? In fact, that's a good exercise to try. Just get out Mathematica, get onto your computer, plot, just work out these terms here. Mathematica will know all of the terms in this Taylor series. And calculate the partial sums. It's ridiculous. And that's because Taylor series have a terrible, terrible time trying to represent the function everywhere in the complex plane. It's too hard for Taylor series. Poor old Taylor series. Okay. So this is, in fact, it's a little bit like the rabbit and the, do you know the story of the tortoise and the hare? Do you all know the story of the tortoise and the hare? The hare, they're having a race. The tortoise wins in the end. The Taylor series converges to the exact answer. But it does it very, very slowly. The asymptotic